Hello, my name is XIANG. I'm from Group Hello. This group consists of 5 persons, including me. So my fellow teammate is Azizah, and Sofea, and also Azizah. In this presentation video, we're going to talk about details of process coordination. At first, we're going to talk about what is process coordination. Process coordination deals with mutual exclusion and synchronization. For a simple word is, in a multi-process system, process coordination is about coordinating the exclusion of processes in a way that no two processes can access the shared data and resources at the same time. So this means that the process coordination is to reduce the confliction between multi-processes access the data at the same time. So my fellow teammate Anis will talk about Peterson algorithm, and also Azizah will talk about the semaphore, and also the WENG will talk about the producer-consumer problem, and the XIANG will talk about the solution for the producer and consumer. So let's get started.
Okay, Assalamualaikum and hello everyone. I am Sofea from Group Hello. So we will go through about Peterson algorithm. Okay, Peterson algorithm is a simple algorithm that ensures one mutual exclusion into one resources. Okay, and here it will have two process. Okay, two process here that will share two variables. What is the two variables? The integer turn and also the boolean flag. Okay, so what it will turn do? Okay, so turn function will be whose turn will enter the critical section first. Okay, which means that we have two process. It's either turn for process 1 or process 2 that will go through the critical section first. Okay, flag. So flag, what will flag do? It will indicate if the process ready to enter the critical section. Okay, so flag, it is a boolean, so it has to whether it's true or also false. Okay, so here we can see the process. We got several section, entry section, the critical section, exit section, and the reminder section. And the algorithm will be happen in the entry section. Okay, which means that we have two process. Let's see here. Okay, we have process 1 and also process 2. Okay. So process 1, flag 1 equal to true. Okay, it's turn 2. So while flag 2 and turn equal to 2. Okay, and then it will go to the critical section. Okay, and then after that flag 1 false. So it will go to the next process, which is process 2. Okay, so it will be repeating the same like this. Okay. We also know that the flag 1 and flag 2 will be shared variables, which means the process 1 and process 2 has the shared variable, which means flag 1, flag 2, and also turn. Okay, what is the disadvantages of Peterson algorithm? Okay, Peterson algorithm, it will involve busy waiting, and also it only limited to only 2 process, which means if we have 3 process or more than that, we cannot do the Peterson algorithm. Okay, got all of that? Okay, if not, so no worries. Okay, we have the question time. So how do Peterson algorithm avoid the race condition among the two concurrent threads. Okay, so we got thread A and also thread B. Thread 2. Okay, so here flag equal to 2, turn 1, while flag equal to true and turn 1. Okay, and then we go to the critical section and then flag false. Okay, so we go to thread 2 and also the process will be repeating. Okay, what is race condition? It means that the condition when one or two or more process want to perform at the same time. So Peterson algorithm can avoid the race condition. Okay, that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Azizah. What is semaphore? Semaphore is a synchronization tool where it provides more sophisticated ways to synchronize activities. And it can only be accessed by two atomic operations. Atomic means that it cannot be preempted. Instead, when one process can modify semaphore variable S, no other processes can modify the variable concurrently, so it cannot be preempted. And then it is to control access to a shared resources. It is represented by an S, where S is an integer variable, and the semaphore is the signal of the occurrence of an event. How do semaphore sync processes? By using two operations, wait and signal. When semaphore goes into wait function, the wait function in the left side of the slide, another busy waiting is happening, and then the value of S will be decrement. Meanwhile, for the signal section, it does the increment of the value of S. Implementation of semaphore, it has two types, busy and non-busy waiting. In busy waiting, as we can know, no two processes can execute wait and signal simultaneously on the same semaphore. So the implementation of the busy waiting itself becomes the critical section problem, because the wait and signal is placed in the critical section. Since we need to eliminate this busy waiting, how do we do that? It is by implementation of the semaphore without busy waiting. So in the no busy waiting, each semaphore has an associated waiting queue, which are represented by S and Q. So S is an integer where it is a non-negative at initialization, as I mentioned before. At start, it is always initialized as 1. And then for the Q, Q is represented of queue of processes threads, where it is always starts as an empty. And then the implementation for no busy waiting, it is implemented by two functions, wait and signal. In order to implement this no busy waiting, we need to have mechanism to see who and which will be put in and out of the queue. So these two operations for block and wake up are the mechanism that we need to use in no busy waiting implementation. So when S equal to 0, there will be process in the critical section. So the value of S needs to be non-zero in order to enter critical section. So this is what we want to eliminate. Thus, that's why we added the block and wait function. And then we use Q to allow semaphore to block a process and wait when S is incremented. And then if a process calls wait when S is less than 0, it will be added to Q and block using block operation itself. And then the value of S will be incremented by 1 when the current process in critical section has finished, then call signal. And if the value of S is equal to 0, next processes in queue is fetched using wake up operation and resume. As you can see in the right side of the slide, it is pretty straightforward because to read and understand it. That's all for me. Thank you.
Is a classical multi-process synchronization problem. It happens when we are trying to achieve synchronization between more than one process. Generally, there is one producer and one consumer in the producer-consumer problem. Producer is producing some items, whereas consumer is consuming the items produced by the producer. The same memory buffer is shared by both producers and consumers, which is of fixed size. Both of the producer and consumer have different tasks. The task of the producer is to produce the item, then put it into the memory buffer and start producing items again. While the task of the consumer is to consume the item from the memory buffer. However, there are several problems will occur in producer-consumer. For example, the producer should produce data only when buffer is not full. The producer is not allowed to store any data into the memory buffer if it is found that the buffer is full. Besides, data can only be consumed by the consumer if and only if the memory buffer is not empty. Moreover, accessing memory buffer should not be allowed to both producer and consumer at the same time. Well, let's look at the coding part. The producer code is as following, and the consumer code. And for the count function in either producer code and consumer code, they are extra coding, as listed as below. Well, let's explain some terms of the code above. The first one, the in is represent the next empty buffer, and the out is represent the first filled buffer. While the count in both code is keeps the count number of elements in the buffer. RP is represent the register which keeps the value of M count in producer code, while RC is in consumer code. X is the size of the buffer, and it appears in both the code. Let's see the example of the buffer. In this buffer, the in is 5 and the out is 0. It has a count value of 5 and a size of buffer of 8. Let's start by adding the new element f. It will enter the producer function, and the buffer in equals to item A will make it to make f into buffer 5. And in is now equals to 6 after mod x. Hence, the new buffer list is as below. The f is in the index 5 and the in is now 6, and the out is still remain the same as 0. In the process, the 5 is copied to the register RP, and RP is incremented to 6. After increment and before the execution of the next line, context switch occurs and code jumps to consumer code. Well, let's try to consuming the first element A. It will enter into the consumer function, and the item B equals to buffer out will make it A equals to item B. And the out is now equals to 1 after mod X. Let's have a look of a new buffer list. The out is now equals to 1 and the in is remain the same as the index 6. In the count function, the 5 is copied to register C, RC, and RC is decremented to 4. The RC equals to 4 will store into the count. Hence, the current value of the count is 4, and the context switch occurs back to the leftover part of producer code. Since the context switch at the producer code was occur after the increment and before the execution of the store M count RP, so now resume from here since RP holds 6 as incremental value. So 6 is stored into count. Hence, the current value of the count is 6, which is wrong, as buffer has only 5 elements as mentioned above. The condition is known as rest condition, and it is one of the producer-consumer problem.
Hello everyone, my name is XIANG and I will explain about the solution for producer-consumer problem. So let's start. The problem regarding the producer-consumer process is that they can run concurrently, and to solve the problem we will just apply the concept of semaphore and mutex lock. And there are three semaphores we will use in this solution. The first one is the empty semaphore, which will prevent the producer from adding more items into the full buffer, and the next one is the full semaphore, which should prevent the consumer from taking an item from an empty buffer. And the third one is the mutex, which will act as a mutex lock, and let us see the example for it. So we will look at the initial value for the situation first, and the mutex will equal to 1 is because it will say that there are no process in their critical section yet, so it's a green light to go for them to execute their critical section. And the empty is equal to 6 is because there are 6 empty slots in this buffer, and the full is equal to 0 because there are still not items is inserted into this buffer. And let us look at the first segment of this code. So the first segment is included from here to here. So now the producer will produce an item to be inserted into the buffer, and the mutex is equal to 1 is because the wait function is called upon the mutex semaphores, so it will decrement by 1, and it originally is 1 and now becomes 0, which means that their process are running their critical section now, and the wait function is also called upon the empty semaphores, which will decrement the value of empty by 1. So now it's become 5, and so let us look at the next segment of this code. The next segment will be include from here to here. So now the item is added into the buffer. So the blue slot for this buffer is represent that there are one item is added into this buffer, and as the signal function is called to the mutex semaphore, the mutex will increment by 1, so which means the others process can run their critical section now, and this signal is also called to the full semaphores, and the full will increment by 1, and which original is 0 and now become 1. So now let's just look at the consumer process. So this is the initial value for the process. The mutex is equal to 1, which will enable the consumer process to enter its critical section, and as there are 1 item in this buffer, the full will equal to 1 and the empties will equal to 5 because there are 5 more slots for it to insert into. And now we'll look at the first segment of this code. So now we look at this here to here, and as the wait is called on the full and mutex will decrement by 1. So originally the value for them is 1 and now becomes 0, and the item is removed from the buffer, so the blue slot is replaced by a white slot. So let's just look at the next slide. So we'll show the next segment for this code from here to here. The signal is called to the mutex and empty, so it will increment by 1, and so now the mutex is increased from 0 to 1 and the empty is increased from 5 to 6. So the mutex equal to 1 is to enable the other process to enter their critical section, and the empty is equal to 6 because there are 6 slots for the buffer for now. And so I think that's all for the example, and thank you.
To summary that, no doubt, process coordinating play an important role in multiple processor systems. If without process coordinating, the process may face confliction and delay problem during access the resources. This is because multiple processes are running together, and more than one processes try to access the resources at the same time. This can lead to inconsistency of shared data. To conclude that, while executing many concurrent processes coordinating helps to maintain shared data consistency and cooperating process executions. Processes have to be scheduled to ensure that concurrent process access the shared data without inconsistency. At the end, thank you so much for your attention and interest. Thank you.